nonperturbative structure of quantum gravity vacuum. Or yours, Samir.
Okay, thank you very much for the invitation. Can you hear me and see the slides clearly?
Yeah.
Okay, good. So I would like to tell you about some things we are thinking about, what we have learned from black holes about quantum gravity. And these are going to be very schematic ideas because in some sense, we don't understand them very clearly ourselves. But I think these are the direction forward in string theory to put together what we have learned from this deep puzzle of black holes, and then to apply them to the problem of cosmology, the Big Bang, and all the issues that we don't understand. So I'll try to give you some kind of very intuitive picture, which we have been trying to put in our minds about what we have learned from all the work through fuzzballs in resolving the information paradox. And then we want to see what it can tell us about resolving all the puzzles that we face in cosmology. So, okay, so our conventional picture of the vacuum is that quantum gravity effects will be relevant at small distances like Planck length or smaller, and that's a very small scale. And at that small distance, all kinds of hell breaks loose. But at larger length scales than Planck length, we expect spacetime is basically smooth. We can essentially use the semiclassical approximation, which just means small fluctuations of gravity around a smooth classical background. Now, this is a picture which is very comforting to you because quantum gravity doesn't bother us in our everyday life. But this picture can't be correct because it leads to the black hole information paradox. As Hawking showed us, the horizon of a black hole is a smooth place, but there then you get a creation of entangled pairs by the Hawking process, and the entanglement of the radiation with the remaining black hole keeps monotonically rising, and that creates a problem at the end point of evaporation. So in recent years, the Hawking argument has been made more and more rigorous, and in fact, you can now make it into a rigorous theorem using this small corrections theorem. And the rigorous form, just put to paraphrase it in words for the present context, is if semiclassical dynamics holds to leading order, it can always be small corrections from quantum gravity. If semiclassical dynamics holds to leading order in any region of spacetime where the curvatures are low, which means the curvature radius is much bigger than Planck length, then there's no resolution to the information paradox. Or more precisely, you will either have loss of unitarity or you will have remnants. So you can still have remnants if you think that's a satisfactory resolution. You can still have that, but you'll have either information loss or remnants if you assume that semiclassical dynamics holds to leading order if the curvatures are low. So something has to go wrong somewhere. We also have many puzzles with cosmology. Why is cosmological constant so small? What gives us the energy to drive inflation? Why are the Hubble constant values somehow not quite agreeing in observation these days between high and low redshift observations? In some way, if you put together these questions you get in cosmology these days, they're all connected to the dynamics at the scale of the cosmological horizon. So the horizon radius is defined by saying the H inverse is the Hubble radius, the horizon radius. So H square is proportional to the energy density with this constant. And if you look at the scales you get in cosmology, if you look inside one Hubble radius, inside one horizon radius, and you take this rho and you integrate it all over, the total amount of mass inside one horizon is just about the right order to make a black hole with radius equal to the cosmological horizon. So you might think that the issues that you might learn about how semiclassical physics is not valid at horizon length scales in black holes may then also tell you that you should be concerned about things which happen at the cosmological horizon scale because similar dynamics may appear over there. And all these issues which I mentioned here are somehow, if you look at the energy density that you're talking about, which is creating difficulties, it's something again at the closure energy density scale. So what we'll see is that what we learn from black holes about why the semiclassical physics breaks down in black holes at the horizon scale will then allow us to turn around and say, well, something interesting can happen at the cosmological horizon scale, which is not something we expected by just using the semiclassical equations of gravity and plugging them into Einstein's equations. Okay, so that's what I'm just putting down here on the slide. The semiclassical dynamics of gravity tells us a dust ball will collapse go through its horizon, the light cones turn in, and then matter must keep compressing in because the light cones go in. The matter has to just keep compressing and goes all the way to the singularity. While if you look at the cosmology at a given time slice, here H inverse is the horizon radius, and the way the horizon radius is defined, well, at that time, you will see that the light cones, they point purely outwards. It's just a time reverse of the black hole. Here, this horizon light cones point purely inwards. Here, they just point purely outwards. And as you go further out, they go more and more out. Like here, you can't even stand in one place. You must go in. And out here, you can't stay at the same proper distance from the origin. You must go out. So just under time reversal, it's the same kind of physics. So we can think that whatever we learn here might have implications here. So let's see what we're going to do in this talk. That first we'll see how the fuzzball paradigm resolves the information puzzle. But in the process, we'll see that the quantum gravity vacuum has a very different structure from the conventional picture that we might have. And again, the conventional picture says that you have crazy stuff at small distances, but everything is fine at long distances. Nothing interesting happens there. So what we argue is that the vacuum has virtual fluctuations of black hole type states of all different radii. So you should think of this more like a system which is at a second order critical point where you have fluctuations of all sizes. And they are important. If you are away from the critical point, you have fluctuations, for example, in an Ising model away from the critical point, only on the scale of one lattice spacing, and otherwise everything is basically, let's say, all spins up. And that would be like this situation where fluctuations are only at the scale of the Planck length. But if you're at the critical point, you have fluctuations of all sizes. You get domains of all sizes. And that's what we'll argue the quantum gravity vacuum is actually like. And you might think that these large fluctuations would be suppressed, but in fact, they are not suppressed. And pretty much for similar reasons to what you get in the case of the Ising model, the critical point, which I mentioned, the entropy of these fluctuations, the number of possible configurations you have with fluctuations of a given large size, is given by something which you can estimate using the Beckstein entropy. And as we know, the one miraculous thing about black holes is that their entropy is very large, much larger than, let's say, a star with the same mass. We've known this fact since 1972 when Beckstein told us about it, but we never have any great importance to the actual value, what we do with that thing being so large. But now we'll see that what it does is, allow us to realize that the vacuum actually has a very different structure. And in fact, there are fluctuations of virtual fuzzball type states of all sizes, and realizing that you have this second order phase transition kind of structure of the vacuum, and not like this kind of picture of the vacuum, which is like something away from a phase transition, that is essential to solving the information puzzle, but it'll also turn around and tell us that something interesting may be happening in cosmology at the horizon scale. Okay, so I'll try to go through the essential idea, and this part is really very schematic because we ourselves understand it only very schematically. So if it's not precise, I apologize in advance. So we'll go through some toy examples. And so let's start with the toy example where the universe is just in a stationary state, not expanding, some fixed, flat space-time. And there's some time t equal to 0, t equals t naught, the universe starts to inflate. Say at the gut scale, something falls into a new minimum and the thing starts inflating at the gut scale. Okay, so if you don't think of any vacuum fluctuations or anything funny, you would just solve the semiclassical equations and you would get the expansion rate. Put in the energy density, let's say coming from a scalar field they inflate on, and there that would be your equation. But think of the QCD vacuum. Again, this is all a toy model. We're not going to say that this is actually what is relevant, but just to understand the idea. So before the whole thing started inflating, we were in the vacuum of normal physics as we know it. So in particular, you have the vacuum for the fields involved in QCD. And QCD contains a bound state excitation called the meson. You have a quark, anti-quark, and then in between there's a flux tube of gluons like a string. The whole thing has a length scale, something of the order of the strong physics scale, let's say 10 to the minus 13 centimeters, 1 Fermi. There's such an object in theory. And what we're now going to ask is, well, of course, you can make a meson if I give you 100 MeV, but suppose you are in the vacuum. Well, the vacuum is not actually empty. The vacuum contains virtual fluctuations. And let us ask, would it not also contain virtual fluctuations of meson type configurations? If meson is an actual object in the theory, you would also expect virtual fluctuations of mesons. We'll have to think a little bit more, and we'll come to that later as we progress, what this might mean. But of course, this is something we are very familiar with. Just like You can have a real electron and a real positron, but you also have vacuum fluctuations of E plus E minus pairs. In fact, they are what give rise to Hawking radiation. We are now asking, do you also have virtual fluctuations that correspond to something like the positronium? That's also a bound state. It's an object in the theory. And in particular, right now, I just took the meson because here I have the QQ bar. It's joined by a string. This is a picture I pulled off the web of the way they have done numerical simulations on the lattice for the QCD vacuum. In fact, they see virtual fluctuations of gluon flux tubes and the like. So you can actually see these things on the lattice. But for the moment, let's just accept that we have virtual fluctuations of meson type configurations. And when I draw a virtual fluctuation, I draw it a little faint as compared to a real on-shell meson, and I've actually given you the energy to create an on-shell meson, and then I'll draw it without making it faint. Okay, now if you take this universe and it was expanding slowly, and it grew from this size of the box to this bigger size of the box, well, nothing very dramatic happens. What will happen is that now you have more volume, but the number of virtual meson fluctuations you expect per unit volume would probably still be the same. So I've just drawn more of them. Every little spot that you have in the universe, long back, a universe was very small. Today, it's expanding. So in another 10 to the 10 years, we double the size. But we don't expect any very dramatic effect of these mesons. There'll just be more volume. So more of these virtual fluctuations, they are everywhere. But that's not what our toy model was doing, the one we were looking at right now. We said the expansion is at the gut scale. So in fact, the horizon radius is the gut scale, which is 10 to the minus 28 centimeters, which is much smaller than the size of the meson, which is set by the strong physics scale. And then what happens? Well, schematically, the picture is like this. The horizon now is 10 to the minus 28 centimeters. That's the gut scale. And the virtual fluctuation which I had in the Minkowski space I had before I suddenly started inflating, well, that had this particular meson, which has a size of 10 to the minus 13 centimeters. Of course, nothing is to scale here. But you can see that this is far outside the horizon. And let's try to imagine, because we can't actually calculate this, let's try to imagine in our minds, what do we think will happen? Well, this quark, because the light cones point this way, is forced to go here. This quark, because the light cones points purely outward, it's forced to go here, and the whole object is forced to stretch. So in fact, this virtual fluctuation can't immediately disappear. Just causality tells us that in fact, this whole thing will stretch, and the stretching actually will, of course, cost us energy because the flux tube is actually being stretched. So in fact, as things start stretching, there's going to be an extra energy. It's not just for the meson. Similar effects have been studied if you look at effect of virtual strings. So if you had a virtual string loop, which was bigger than the horizon size, and then the universe starts inflating with some small horizon size, and this virtual string was actually bigger than the horizon, it would actually get stretched because in fact it can't shrink and disappear because the light cones point purely outwards and it can't come in. Okay, so but let's just stick with the meson because I'm making a toy model right now. So what we're going to say is that there's this extra energy that we see here. We would not have thought about this energy if we didn't think about the structure of extended objects in the vacuum. So there is an extra source of energy that we would have missed. We're not going to say this is important. I mean, if you actually try to look at the real universe and you're trying to do physics at the gut scale, the universe was in a big bang at a very hot temperature before inflation, and strong physics wasn't really relevant. So this is a toy model, but it brings out the essential idea we're going to push at, that if there are extended structures which are present on shell in the theory, extended structure just means something with a size like the meson, they're also present as vacuum fluctuations. And if you have a horizon which is larger, which is smaller than the size of that structure, then because the structure of light cones, there's an extension, or in the case of black holes, a compression of the extended object that actually notices the structure of the existence of a horizon. So one thing we've always wondered about horizons is that physics can't see horizons because horizon can't be understood locally. It's something very global. It's a topology, something all around. If you go to any one point in the horizon, there's nothing to see there. It's something, but anytime you make a closed trap surface, there is something physical. If you put the whole horizon together, the light cones point purely inwards or purely outwards all over the surface. And what we'll see is these virtual fluctuations of extended structures, they do respond to the presence of a closed trap surface. And we'll come back and see this is what we think resolves the information puzzle in the fuzzball paradigm. And this will then also tell us some interesting things about cosmology. One by one. So vacuum fluctuations by themselves, of course, have been studied a lot. So if you don't think of extended objects for the moment, just think of Fourier mode of, let's say, a scalar field. Then when the cosmology expands, the Fourier mode wavelength gets stretched. It's a known effect. It just gives you particle creation in cosmology. It's not a very big effect. If you compute the back reaction from created particles, it's a small fraction of the total energy density, but the effect is there. So we understand that these things happen, but just the particles there are not all that important. Our present interest is in the behavior of vacuum fluctuations that form extended structures, which have a size. So we'll talk about this word extended quite a bit in this talk. So let's review the role of such extended structures in resolving the information puzzle in this fuzzball paradigm. So let's first go back and recall what is the information puzzle. So if you think of a graviton moving in Minkowski space, this is just my picture of a graviton, let's say, going to the right. By Lorentz invariance, it just continues to move without change. It's going in a straight line, just keeps going. So we know that. Now take two gravitons, they're heading towards each other. They move at the speed of light. But by causality, neither graviton knows the other guy is coming. So in fact, all the way till they actually collide, they just keep moving, without any change. In fact, you can make a shell of particles coming from all different sides. Let's take 4 particles coming this way. And in fact, you can check that if they're all moving at the speed of light, no signal can actually propagate from this particle and actually reach that particle. Because they're all moving at the speed of light, by the time a signal reaches here, it will go there, but it won't actually reach the particle. The particle already have moved. So in fact, no particle actually knows the other particle is coming. So in fact, no light ray can reach from one particle to the other. And so all the particles smoothly move through the radius, where the total mass of these particles would have actually been enough to create a horizon. This is the usual argument of the information paradox. As things move to the horizon, nothing happens. And if they are null particles, you can even try to argue that by causality. Once your shell of particles has been inside the horizon, the light cones point purely inside. And even though new dynamics can always happen when curvatures reach Planck scale, this actually cannot affect what's happening near the horizon. That's where Hawking told us that entangled pairs are created and create the entanglement problem. But because the light cones point inwards here, no effect from here can actually reach out here just by causality. Okay, so this is what I drew here. The effects actually can't go there. If you assume causality, all the space here is gently curved, so it can't come to it across the light cones in this region. So then people wondered, would it be possible to solve the information puzzle by the idea of small corrections? Even though in semiclassical spacetime, which is what all this region appears to be, you can't have anything coming out of the light cone like this red dotted line. There could be some small quantum gravity effects that might actually leak outside the light cone. And then the correction to each pair might be small because the quantum gravity effects are small. We are assuming if the space is gently curved, but then the number of pairs you produce is very large. So could there perhaps be some delicate correlations among these pairs? And could that perhaps remove the problem that our entanglement is growing? Maybe it could make the entanglement come down when enough of these pairs have been produced. But a small correction theorem tells you that actually this is not possible. If the correction to each pair is bounded by some epsilon, the entanglement of step n+1 after n+1 particles have been created exceeds the entanglement of step n by log 2 minus at most 2 epsilon. So even though the graph may come down by 2 epsilon at each step, it can't stop increasing, and so it doesn't actually help you solve the puzzle. So put together, this is what makes the Hawking argument precise, that there is really no way out of what Hawking told us if you take the assumption that you have semiclassical gravity in all regions of gentle curvature. That's all the way up away from this region. If semiclassical physics holds, and the causality, of course, is part of semiclassical physics, there can be small corrections, we've allowed them, but it doesn't allow you to get out of the information puzzle. So now we have this information, the rigorous form, which we can now again state schematically as following. If semiclassical dynamics holds leading order in any region of space-time which is gently curved, then the theory must necessarily have information loss or remnants. Okay, so we want to know which step in this analysis of Hawking actually goes wrong. So we have been looking at the effect of virtual excitations in this toy model, which are these virtual mesons. And let's see how these effects would change black hole dynamics. Okay, so we were talking about the standard QCD. We're still making toy models, so let me just talk about QED. So in QED with protons and electrons, you can make atoms, you can also make a benzene ring. I'm just having fun, so I can look at anything. None of these will actually be the physics we finally want, but the ideas would be there. So the benzene ring is an actual thing.
Sorry, Samir, I think there's a question.
Yes.
Stop.
Go ahead.
So, Samir, on the previous slide,
1 second. Yes.
Aren't you also assuming that the locality is exact? Not just, I mean, it's not just that something holds at leading order, but that also there's exact locality, including non-perturbative effects?
So no, I don't think so. So let's see, if you try to put non-local effects on the scale of the black hole horizon radius, that doesn't matter to the argument at all. So that's irrelevant. I think what you're probably asking about is non-local effects between the black hole and all the way out to infinity, where the radiation. So let's talk about those possibilities. So if you have non-local effects all the way out to infinity, okay, and if those effects are also small, it doesn't change the argument. So if you do anything at infinity which preserves normal physics at leading order, it won't do anything for you. So the only thing which is excluded here, by which you can get the information out while still preserving, let's say, a smooth horizon, is that if you give me a non-local effect, which is non-local interaction between the black hole and the particles at infinity, which can modify the particles, even the ones which have been emitted in the past, for arbitrary long time. So it's a small effect in any given time. Let's say in one evaporation time step of 3 kilometers time, the effect is small, but the particles are going to be emitted over 10 to the 10 years, 10 to the 120 years, or whatever. The small effect, if it continues between the black hole and infinity for 110 to the 120 years, that can flip spins in a way in which you can try to restore unitarity, right?
So I think I disagree, because non-perturbatively, you can't even talk about particles near the horizon. So I think I disagree that you're implicitly assuming something about that being non-perturbatively exact.
So let me see. Actually, I'm not sure I understood. I didn't actually say that I need to understand anything about particles around the horizon, or in fact, let's take the entire region inside some region like 10M, okay? I don't need to know anything about that region. All I need to know is that whatever junk is going on there, suppose you could make what people talk about these days, a code subspace of this complicated junk in which you could effectively see some semi-classical dynamics, which allows you to see semi-classical evolution for a few pairs. At infinity, I'm assuming physics is normal. If I go sufficiently far away, suppose I assume that physics is exactly as given by the textbook of Polchinski. Given this, you cannot get out of the puzzle. Let me put it very strongly that way. If you now want to say that there are, at infinity, physics is not the one given in the textbook of Polchinski, there can be some non-local interactions from this entire region inside 10M. I don't care about it being written in terms of particles or anything. If I want to have some effect from this entire region inside 10M all the way to infinity, so I don't have normal dynamics at infinity, that if you have interactions from this region all the way to infinity for arbitrary long times on all the particles, then there's a toy model we have given in our papers. We can allow you to flip spins in a way that the entanglement gets removed. Okay, absolutely, you can do that. So that would be different from the way the black hole radiates compared to a piece of paper, because when a piece of paper burns, once a particle leaves a few meters away from the paper, it's not influenced anymore. But if you do want to make a model where this influence exists all the way to infinity and at all times, then we have given bit models where you can do that. So I'm assuming that you have normal physics at infinity and not normal textbook string theory at infinity. Yes, I should say that. And so that's what I actually meant by semiclassical dynamics at infinity, but I should add very much that, which I should have said, at infinity, I assume physics is normal, and then you can't. Okay. So what we want to answer is, this has always been the standard question with the information puzzle. The previous steps I gave you are basically the information puzzle, and the small correction theorem just makes it precise. So the question is, which step goes wrong? And so we have just been talking about the virtual excitations of these mesons and so on. And then we said, okay, let's talk about some structure like the benzene ring, still a toy model. Because you can really have a benzene ring, the vacuum must have virtual fluctuations corresponding to the benzene ring. It's not yet clear what it means to have a virtual benzene ring, but I'm going to be talking about that. But suppose I now take a mass, which I have drawn by this red dot. It's not dense enough to make a black hole or anything, and I put it in the middle of the benzene ring. You could imagine another atom sitting there, for example. The gravitational pull of this, what will it do to the benzene ring? It'll slightly compress it. It'll sort of come in a little bit, slightly compress it, but then it'll just stabilize, because all the atoms also repel, So it'll also stabilize and nothing much happens. But now suppose you consider such a fluctuation inside the horizon of a black hole. So you can see the light cones have turned inwards. And now what happens to the benzene ring? By just causality, this ring has to keep shrinking. Whatever might be the repulsive force between atoms once they are brought closer than an angstrom, that's what stabilizes the ring normally. It doesn't help this time. It's going to crush, and the wave function of the ring will deform by order 1 or more. At that point, for reasons which I'm going to just again schematically sketch the following slides, one argues that this would now not be a virtual excitation anymore. When you deform virtual excitation by a large amount, by order 1, when they deform the wave function by a large amount, they can become on-shell excitations, and suddenly you'll find some structure. It's not the benzene ring, it's sort of pretty damaged by now. I just drew it like that, but it's something else, which just pops out of the vacuum. And now you will see that something just popped out, which you would have missed if you had not realized that these virtual structures were actually there in the vacuum. Okay, so just to understand all this better, one has to know what are virtual fluctuations. We're talking about these schematic things and we're just drawing these pictures. So let's talk a little bit more about what virtual fluctuations are so we can put these ideas more concretely in our mind. But let's say the important thing which has been done by drawing this benzene ring, let's not miss the main point. An extended structure like this, it sees the existence of a closed trapped surface. It gets compressed if you have actually got effects coming from all sides. If the light cones tilt in from all sides, you can see the structure is actually getting compressed. It is this kind of object which sees the formation of a closed trapped surface, and this physics you see will be essential. In fact, if you don't have such structures, then using the theorems, the small curvature theorem and so on, one can prove, as I had said before, that if you assume there's what effect I'm going to tell you now, suppose you say, no, these effects don't do anything or anything significant. In fact, there is no solution to the information puzzle, which will then allow you to preserve 1, unitarity, and 2, normal lab physics at infinity. So I will go to state it as a rigorous, I'm not trying to prove it here. I'm going to state it as just a fact. It is going to be rigorously true. If you want to keep normal physics at infinity, just out of textbook Polchinski string theory at infinity. So as you go sufficiently far, all effects fall off to leave you with that physics at infinity. And if you want unitarity, even in the black hole region and everywhere, the whole thing is unitary. There is no solution to the which is possible except along the lines which I'm giving you now. So that argument is not here, but you can see it in the papers, and anyway, we can talk about it later. So it's important to focus on what happened here. So let's understand virtual fluctuations a little better and see what is a virtual fluctuation. So just take a pendulum. Let's go back to the harmonic oscillator. Classically, the ball sits at the bottom. Call this coordinate x, sits at x equal to 0. Now here's the potential of the harmonic oscillator. Quantum mechanically, the wave function is not sitting at x equal to 0. It sort of spread like this because the gradient term in the Schrodinger equation, the Laplacian term wants it to spread. And the potential wants it to come up. So it's spread like this. And the fact it's away from 0, all this part under the barrier, where sort of, the momentum is p square is negative. That's the region which we call a virtual fluctuation. So that's all I'm going to say is a virtual fluctuation. Just spread of the wave function in regions where its momentum squared is negative, which is all the region where it's under the barrier, which means anywhere away from the classical configuration. Okay, so when the pendulum is here, all these things contribute to the wave function. You can see I've drawn it faintly as opposed to drawing it solidly because this is the virtual fluctuation. We have to think exactly quantum mechanically or quantum field theoretically. The entire wave functional of everything in quantum gravity should be at the back of our mind. And the whole idea is going to be that quantum gravity wave functional has a lot of parts which are under the barrier. Normally, when we think of semiclassical physics, we think of the part where the classical physics is there, which is inside the potential well. But there's a part of the wave function that leaks under the barrier. Now, if there are many, many directions in your space of configurations, and the space of quantum gravity is huge, and in particular, once you get to the domain of fuzzballs, which are states which can be formed with a given mass around inside the region of a black hole, if you have a very huge family of states possible, a very large part of the wave function is under the barrier. We will argue this under the barrier part, which is what we are calling virtual fluctuations. That is like these virtual mesons we talked about. We will say it corresponds to extended structures, which of a kind which I'm going to show you. And it's the dynamics of the extended structures and their compression inside a closed trapped surface, which will actually give us the clue as to how we are getting out of the otherwise completely tight information puzzle. So I'm just mentioning this outline again and again so that we don't get lost in these random things which I keep drawing. So we just saw what a virtual fluctuation is. And I also kept saying, if you're inside a horizon, the virtual fluctuation field gets squeezed. It's almost as if I'm treating like a real guy which gets squeezed. But actually, virtual fluctuation do respond to forces just the way real guys do. So if you just apply, say, electric field, put two parallel plates, they're like a mesh. We assume this ball can go through. Okay? So the ball is made of something which can go through the thing which is applying the field, some electrodes. But here's an electric field. And if you look at the wave function, it had this potential I had before for the pendulum. But if you apply the electric field and you give this ball a charge, let's say a positive charge, then the potential actually in this region sort of goes down. It becomes linearly going down potential. The potential. I just didn't draw this very well. The wave function is what starts oscillating. It's not very well drawn. But anyway, what happens is that the potential in this region goes down. And if you look at the actual wave function, we start with a normal wave function like this. It goes like this, and then actually gets an oscillating piece. You can just evolve the wave function, the harmonic oscillator. So yes, you can think of virtual fluctuations at the back of your mind intuitively. They behave pretty much like normal things. It's just like if the object is here, you apply electric field, the wave function evolves as the ball gets pulled further to the right. The wave function gets pulled further to the right. And if you pull it enough, it even becomes on shell, which means the p squares to become negative actually becomes positive. It actually becomes oscillatory. Okay, so of course, virtual fluctuation we study a lot in gravity because they lead to from like the Hawking effect, the Schwinger effect. For example, the Hawking effect, if you look at a scalar field, then each Fourier mode of the scalar field is basically a harmonic oscillator. And then what are the virtual fluctuations of the scalar field? Well, all this part of the wave function, which is under the barrier, where the pi square is 0, for each Fourier mode is one harmonic oscillator, and the potential for that V of phi k I've just plotted like this. So we know the Hawking effect comes up in the following way. You start with every mode phi k of the field to be in the ground state. That's what I have drawn here. So there, the initial mode labeled by I is in the ground state. But then if you suddenly change the potential, so that I've just drawn it pretty much flatter here, the wave function doesn't respond as quickly. So the wave function is still there. If you try to expand this wave function in terms of the states of this new potential, you find it's not the vacuum state of this final potential OF, but also contains a mixture of the two particle extension, the four particle extension, so on. And this is the formula of phenomena of particle creation in curved space. And a particular example of this is the Hawking effect. So of course, we understand about wave function and the potential is changing, and then the vacuum just giving rise to on-shell particles. And that happens whenever a potential changes and the wave function distorts by order 1. If it was the vacuum before, now it contains pairs of particles. Okay, now we're talking about extended objects. So those pairs of particles that we studied the Hawking effect, they were just like single particles, single quantum scalar field. They're not like extended objects in any way. But now we're interested in, like, if you have an on-shell meson, we have a virtual meson. What's the meaning of a virtual extended object? Can we have a mental picture of that? Well, the Hawking effect involved fluctuations of E plus E minus pairs, but as we said before, the theory also admits the bound state, the positronium. So what's the meaning of a vacuum fluctuation of a positronium? Okay, so for a scalar field, we drew just, for each mode, we drew just one axis for a real scalar field, and the wave function is a function of phi k. It's the Gaussian wave function. If you think of E plus E minus fluctuations, again, for the moment, ignoring any interaction between them, the interactions will make the positronium, but let's ignore the interaction. If you ignore the interactions, well, let's describe the E plus field this way and the E minus field this way. And then this Gaussian wave function I drew, let me draw it on this two-dimensional plot. I can draw it like a contoured plot now because I can't draw this in a three-dimensional curve surface. So I'll draw it as a contoured plot, and you can see the function will just fall off, will peak in the middle and fall off on the sides. The potential goes like a fruit bowl, and the wave function falls off in spherically symmetric contours. But in fact, we know there is an attraction between the E plus and E minus. And what that does is, it says that the potential is lower when the E plus is near the E minus. That's what the potential means. And when they are away from each other, the potential is higher. So if you put that in and then you actually solve for the correct wave function, you can see the actual wave function will have contours like this. When E plus is close to E minus, that's you're along the diagonal, then there is more amplitude for the wave function. Okay, we can just picture all this. So in fact, that's all we have to think in our mind about what is the meaning of a virtual bound state. A bound state, virtual bound states are just words. In the end, the only thing we have is the complete wave functional of all the fields in our theory. This wave functional is a wave functional living in a very complicated potential. And the potential exhibits all the attractions and the forces that are there in the object's theory. And if there's some forces which lead to a bound state like a meson, for example, well then it just means when the Q and Q bar are close to each other, there is a lower potential. So there's a bigger wave function there. And that's all. The wave functions are peaking more in regions where the potential is lower. That's whenever we say virtual particles behaving, responding, ultimately all I'm trying to talk about is that complete wave functional. Everything else is just pictures. Okay, so this is the summary of what I just said in the last couple of slides. If there are interactions in the theory that produce bound states, then this fact shows up in the potential on the space of field configurations, and the potential is lower when the quanta at a given distance where the bound state is, and the potential in turn governs the vacuum wave functional. There's a larger amplitude when the quanta are close to each other at that given distance other than otherwise, and that's what I mean. That's exactly what I mean when I draw these pictures, just telling me about that wave function. Okay, so now let's take a brief tour through fuzzballs on which, as I always say, lots of people have worked. This is, I'm really writing the work of lots of people. This just in a couple of slides, and then we'll come back to what we want to do with fuzzballs. Just to remind you about the story of the fuzzballs. So thermodynamic arguments have told us that black holes have this entropy, and then you could ask, can you reproduce that from a microscopic count of states? As Strominger and Waffa did that. They took some D1 branes, some D5 branes, and some momentum modes, and they wrapped them in this particular way. These on S1, these on S1 cross T4, these momentum modes going along S1. They made a bound state of this, and they counted the degeneracy of this bound state. How many states can you have with these same charges? And in fact, when they did that, they found that when they take the log of the number of states, then in fact, the microscopic entropy there is equal to the entropy you get from the area. So it tells us that we're on the right track. We basically just need to understand these states better, because the calculation for these, the counting of these was not done by actually making these wave functions, but either using an indirect index argument for the extremal case, or using a weak coupling calculation for the non-extremal or near extremal cases, and then just assuming it works for stronger coupling. But in any case, the weak coupling case had no trouble with unitarity, just a bunch of strings and branes. If you take this picture as strong coupling, you'll be back at the information puzzle, because as we said, that will create your information pairs. So really the question was, what does this weak coupling state look like at strong coupling? It's not string coupling, it's strong coupling. And so then in some cases, one managed to actually construct that. In this case, one can even follow it all the way from weak coupling to strong coupling. And one finds it actually doesn't go over to the standard picture with all the mass in the center and a vacuum everywhere. It just swells up into something which is gets progressively complicated as you look at more complicated states. And all the cases which have been made, you get structures like Kaluza-Klein monopoles. Kaluza-Klein monopoles have a shrinking circle, just a different topology. And then between those shrinking circles, you have topological S2s. There are fluxes on those S2s which don't want the S2 to squeeze. And the whole structure sort of stays there, some kind of a, if you like to think, like a benzene ring. It doesn't want to stretch or compress. It just wants to be a structure. So you take different states out of this Strominger-Waffa categorized the states you could count at weak coupling in the CFT, and you follow them along as strong coupling in the cases where you're able to do it. And all the cases that people have done over the last couple of decades, you always end up with some structure like this, which actually doesn't have a horizon. So it never actually ends up making a horizon. It gives you something like this. And I just draw this always schematically. But this object, in the cases where we were able to compute radiation, it just radiates from its surface like a normal body, not by pair creation at the horizon. And then there was no issue with the information puzzle. You get a normal page curve, and the puzzle just goes away. It's been done for a lot of cases. I just often flash the slide to show what cases. If you have general ways of breaking up the strings into different pieces, at general amounts of momentum put on each string, you get all the states. So one just does it piece by piece. First, if you can break the strings to arbitrary ways, but no momentum, then one knows how to make all the states. If you break it into the different pieces, but put the same amount of momentum and anti-momentum on each of them, well, that also makes it easy. So those ones you can make. And so there are lots of cases that one can do. And so lots of limiting cases have been studied. And in each of those cases, you actually found the fuzzball. In principle, one could have still argued in earlier years, and some people did argue that, okay, these are all special limiting cases. And suppose you make the most generic one, maybe that guy has a horizon, or something that can be approximated by a horizon. But in fact, that's what a small correction theorem tells you, that if that one does have a horizon or can be approximated to leading order by a horizon, you will never get unitarity. So in fact, the picture we have in our mind, we make all these extreme cases, then use a small correction theorem to argue that even the stuff in the middle, which is a complete mess, which don't try to make. This picture is sort of like the one we make for M theory. We study all its limits like 2A, 2B, zero theories, and so on. In the middle, we know there's some mess, but we try to get our intuition by studying all the limiting cases. But here for the middle, we have at least this small correction theorem, which tells us that if you actually don't have a fuzzball, you will actually have, again, the trouble with the information puzzle. So yeah, for now, I'll just assume for the rest of this talk, I don't really want to talk about the fuzzball structures in detail here. I'll assume everything is a fuzzball, and let's see what that does for me. So this resolves the puzzle of how the black holes radiate without creating the problem of blowing entanglement. But actually, we can learn something very profound by taking another careful look at the original puzzle. Remember, the puzzle was this. These particles are coming in at a speed of light. So they don't know that each of the other ones is coming in and they pass through the horizon. Then the light cone structure turns in, and even if funny dynamics can happen at a singularity, it can't affect the outside, at least the semiclassical leading order. If it does affect a little bit at some quantum gravity effects, the small correction theorem tells you that won't help. So here was the complete argument. Which step goes wrong? So the whole question is, if you have a collapsing shell, let's look at the dynamics. Look at the dynamics now. So if you look at the static structures one by one, we now know earlier we had the no-head theorem. People thought they could get no structure at mass m, which would actually not all fall to the center. Everything was squeezing. You had for example, all this theorem that if you come with a certain radius, the horizon 2¼ m, like the Buchtel theorem, it'll have to suck you in, and so on. But now we know these fuzzball structures, they have a non-perturbative structure, which can basically be summarized as following. There are compact dimensions. In this case, the one I made for the D1, D5 system, there are 5 compact dimensions. Because they are small, let's say string scale, one might have thought that you should just make a tensor product of those 5 guys with the remaining space. Because they're so small, we dimensionally reduce on them and study gravity in 4+1 non-compact dimensions. But in fact, you can't do that, because what actually ended up happening was that all these fuzzball structures are such that the 5 compact dimensions are not trivially fibered over the non-compact dimensions. There's no net topological charge, but somewhere they may twist in one way, somewhere they twist another way. So they are not a product space. And that's where what all these structures are. When you look at those kinds of structures, you find all the no-head theorems go out of the window. So that's what happened non-perturbatively. The compact dimensions fibered non-trivially over the non-compact dimensions and gave rise to this enormous number of states that the collaboration of Bina, Warner, Martinek, Turton, Justo, Rodolfo Cruz, Shigemoy, all these people have been studying in such great detail. These are all these structures you can get when the Calabi or other compact dimensions are non-trivially fibered over the non-compact. That's where all the hair or the microstates are hiding. And if you first dimensionally reduce on those, you can't see anything. And in a way, you might have expected that in hindsight, because if you look at how the Strominger-Waffe entropy came, it came from the different ways the strings were vibrating in the compact dimensions. So at the brain, it doesn't come so much from the non-compact side. So really, at strong coupling is the compact dimensions, how they how they are locally fibered over the non-compact, which gives rise to all these structures. But now we're asking a dynamic. So looking at these, you can say, okay, now we know the microstates, and then they radiate like normal bodies. We don't have a puzzle. But let's push the envelope and ask, how did this collapsing guy actually go and become this? Because just by semiclassical dynamics, as it passed through the horizon, nothing dramatic seemed to be happening. And once it goes in, the light cone structure would prevent anything changing at the horizon. So what changes? What goes wrong? So this is what we call the vecro hypothesis. It's just a hypothesis based on the pictures we have developed, but also a large part of it comes because one can rule everything else out. So by repeated application of the small correction theorem and seeing what can't help you, you end up ruling out lots of things. And causality rules out a lot of things as well, causality in gently curved spacetime. And using them repeatedly, one comes to the fact that if something like this doesn't happen, you can't get out of the puzzle. So I'm not trying to argue that part here, that you can try to see a bit of from the papers, or we can argue that separately. But let me give you the picture that we have made out of all this. So these fuzzballs, we know they exist as on-shell configurations in string theory because we have made these structures. If these fluctuations then exist as on-shell structures, then the vacuum will also have them as virtual configurations. Now you can see I draw them faint, or I draw them as like these gray bubbles. They're the virtual fluctuations of those structures. You might think that they are not very important if they are big, because they are very suppressed, the action is big. But then if they are bigger, there are also that many more flavors of them. In fact, you can say the flavors are roughly e to the s back, and so a large number of them. So the picture we get of the vacuum is the one I was mentioning at the start of the talk, that what we think is happening is like a second order phase transition picture, where you have these virtual fluctuations of all sizes around all points. And we call these virtual fluctuations vecros for reasons which I'll just make clear in a second. The vecro stands for virtual extended compression resistant object. We sort of talked about all these words separately already. They're obviously virtual because talking of virtual fluctuation, they're in the vacuum. They obviously extended. And as we said, that is crucial to resolving the information puzzle. Only an extended structure in the vacuum can sense the presence, the formation of a closed trap surface. They are compression resistant because, as we said, like a benzene ring, it doesn't want to compress. If you compress, the energy shoots up and the wave function deforms to make it become an on-shell excitation. But the same happens for all the actual construction of fuzzballs that we know. They don't want to either stretch or compress. It's roughly like benzene rings in that form. And the word O just stands for objects. So let's just go through a quick estimate of why the large vecro with the radius, let's say RV, V stands for the radius of the vecro. If it's much bigger than Planck length, why is it not suppressed? And the fluctuation to any large configuration, suppose you estimate it by some kind of an e to the minus the action, the property of the fluctuation, which you can write as some kind of an energy of the fluctuation times some kind of time scale. And I'll put both the time scale, I'll put for the energy, I'll put like the mass, which in Planck units comes out like this. For a black, I'll put a mass of a black hole with that radius. For time, I'll again use the same as a black hole of that radius. So for any mass, I use the entropy, I use the energy and time from there and compute the action. So I'm sorry, I shouldn't have used S. S is not the entropy. When I use entropy, I put the word back in there. This is the action. So the action you find comes out like this. So it's in any dimension. D is the number of space dimensions. And if you estimate the number of these configurations by the Beckstein entropy, so I'm not giving an argument for this, just putting it in for the moment, then you find that these powers are the same. So at least there's a plausible argument that in fact, there is no suppression of these vacuum fluctuations, and a large part of the wave function resides in this part, which is under the barrier. So there can always be some part of wave function under the barrier, but you have made lots of toy models where if you take, let's say, a harmonic oscillator, a square well, but not in one dimension, but in n dimensions, and you take n to be larger and larger, you find that a larger and larger part of the ground state wave function is actually outside the well, it's under the barrier. It just has more space under the barrier, and so more and more part of the wave function goes to the barrier. So roughly that's the idea, that a large part of the wave function is in these virtual things, and we want to know what actually happens to these virtual configurations as the closed trap surface forms. The other part we said was that the vectors have compression resistance. As we already said, a benzene ring doesn't want to compress, but how do you define how much compression resistance there is? Taking intuition from the few fuzzball structures that we do know, if a fuzzball has radius r, and you compress it by a factor of order 1, make it 1 plus delta, I'm sorry, with delta like order 0.1, let's say it's 0.5, how much is the energy increase? That's the way of saying how much it doesn't want to compress. And the energy increase is of the order of the mass of a black hole with that radius. Well, there's only one scale in the problem, so that's the one we'll assume keeps popping up. And so I'm sort of just going to assume, without knowing much about generic fuzzball, generic vecro configurations, that the energy scale is also set by the black hole scale. If you compress a fuzzball by order, a vecro virtual fuzzball by order unity, the energy increase is of the order of the mass of a black hole with that radius. And so this is the picture, just like a water boiling near the critical point has bubbles of all sizes, and the Ising model at criticality has these bubbles of all sizes. We also would like to say the vacuum of quantum gravity has these bubbles of all sizes. The bubbles just mean exactly these virtual configurations of the kind that we have just mentioned, where these compact dimensions are fiber non-trivially or the non-compact ones, and you get structures of the fuzzball kind, which we know to exist on shell. Okay, what's the effect of all this vector structure on the vacuum? As we said, if you take something like a star, which has very gentle gravitational pulls, it's like putting an atom in the center of the benzene ring. It compresses a little bit. Like I've drawn this one a little bit smaller, it gets squeezed a little bit, the vector, and nothing much else happens, and it just stabilizes. And these effects, because they're just reaction of the vacuum to some gentle gravitational fields, they're all included in the effective gravitational low energy theory, which we write through R root minus G, the standard action. Because the response to the vacuum is already in your low energy effective action, so nothing very dramatic happens. But let's see what happens if we actually make a black hole. Our puzzle always was that when a dust ball collapses, nothing much seems to be happening at the horizon because curvatures are low, but then the light cones point inwards, and here's where we had the closed trap surface formation. And so now if you think of this virtual vecro, which is inside the horizon, because the structure of light cones, it has to keep compressing. It doesn't actually have a choice of just stabilizing after a little bit of compression. This distortion then becomes order 1. More of these vectors which just get pulled in, they all keep compressing and just their waveform distorts by order 1. And that's what converts the virtual guys to on-shell guys, very much in the way of the much simpler case of Hawking radiation, where the virtual E plus E minus pairs, where the wave function distorts by order 1, they actually become on-shell E plus E minus pairs. So this is how we think that a picture could be put together, where in the dynamical picture, I mean, the actual hard calculation just show you how to make all these states one by one in the cases where we can make them. But now we're trying to put together a mental picture of what we think happens dynamically. And if we don't have these external objects in the vacuum to react in the way that we have here, you would actually still be caught in the same trouble of causality, small correction theorem, and the information paradox. Okay, so if that is our picture of how the information puzzle gets solved, let's take a few minutes to apply this to cosmology. So with black holes, we said the vectors inside a closed trapped surface, they were forced to compress. Now in a cosmology, if we have any vectors, if they have a radius larger than the cosmological horizon, well, then they'll be forced to stretch. So you can see light construction goes exactly the other way. So they'll be forced to stretch. So, and the energy increase you get, again, the same scale, how much energy will you get from that stretch? Well, if you take something of the order of the horizon scale, H inverse, and you stretch it, let's say 1.5 times the size or something like that, then the energy will be, or the increase will be of the order of a mass of black hole in that much radius. And as because the reasons we said before, if you convert that to energy densities and so on, the energy density you would get from that stretching of the vecro by order 1 would be of the order of the closure energy density. So any effects we are looking for at the closure energy density scale, like suddenly you find a lambda, which you can't explain, which suddenly pops up at some time, which is of order the closure density today, would have an energy of the scale. But the question with that always is, why is it of the correct closure energy density scale today and not of the closure density scale, let's say, at the gut scale? And so we'll see if we can get a possible answer from this kind of effect. Okay, so we'll see that this stretching will be a source of energy for various effects like inflation, dark energy, and so on. But at this point, before we go ahead, we notice an important difference between the Minkowski spacetime in which we made our black hole by compressing a shell and the case of the cosmology. So what is the difference? In Minkowski space, we have these virtual fluctuations of all radii between 0 and infinity. So you can see that all the different sizes are here. And so I've drawn these bubbles of all sizes. They just occupy the entire spectrum of all sizes. This is necessary because otherwise we can't resolve the Hawking puzzle for black holes of all sizes. Because if the vector is only, let's say, up to this size, if you had a black hole of an even bigger radius, you're making it, and you just haven't solved any puzzle at all. So in fact, we saw that you could have these virtual things of all sizes because the cancellation of the Beckstein entropy with the action, the radius just canceled out to work for all sizes. But in expanding cosmology, external structures cannot have a radius larger than the distance that light has been able to travel since the Big Bang. So you can only make an extended structure if light has been able to travel that far. So for example, if you were in the Guts era, where the universe was inflating with the radius of the Guts scale, and suppose light hasn't had time to travel over a distance of 1 angstrom. You could not actually have made virtual benzene rings because for that, the electromagnetic field had to correlate itself over a length scale of 1 angstrom. And if light hasn't had time to travel at that distance yet, well, then those structures don't exist in the vacuum yet. Okay, so let's see what that constraint that imposes. Take a flat cosmology. So here I took a flat cosmology and expanding as some power law. So I put T to the alpha. You can compute the Hubble constant H for it, and then the H inverse gives the radius of the cosmological horizon. The distance that light has traveled since the Big Bang, well, you can just compute that. That's given by this. And this alpha, which gives the expansion rate, well, that shows up in here. And so the size of the vector, the virtual fluctuation, which you get after some time, has to be less than or equal to this R max. If you write as a ratio of compared to the radius of this, the constant of the horizon, cosmological horizon, it looks like this. So you can see that in different eras, where in the radiation era, alpha is a half, and in the dust era, alpha is 2/3, there's a difference between how big the vectors can be compared to the Hubble horizon scale. And we can only form vectors up to radii of that value. Okay, so let's take various cases one by one. In the radiation phase, alpha is equal to half. So you find this radius is less than equal to 1. So in fact, the vectors never actually become larger than the cosmological horizon. And so you can never get into a situation where the vectors are forced to stretch. So you don't actually get this energy of stretching in this particular radiation phase, which is actually good. It's actually important because if you had any extra source of energy of the order of the closure energy density in the radiation phase, then you would have some constraints from the Big Bang nucleosynthesis and so on, which can't be met. In that phase, just the matter energy density has to be pretty much all there is, up to a few percent accuracy. So that's fine, because we are not actually getting any extra energy in that phase, and that's fine. But look at dust cosmology now, where alpha is 2/3. And again, this was the scale we have for how far the vectors can be. And now we find the vector size can stretch all the way up to 2 times the horizon radius. They can, of course, be smaller, but the ones we are interested in are those whose radius is from H inverse up to the maximum they can become 2 times H inverse. And why are we interested in the big ones, beyond H inverse? Because they are the ones which will be forced to stretch. So these vectors, if they are there, they will be forced to stretch. So suppose at some time t0, the radius of the horizon is this, and you start with a radius which is bigger than that horizon, then you have to stretch because the light cones point outwards, and you can sort of compute how far you have to stretch before you can actually, the horizon catches up with you and you don't have to stretch anymore. Okay, so then you can try to play with this a little bit and ask that when the radiation phase turns over to the dust phase, what happens? In the radiation phase, these virtual fluctuations, we are calling them vectors, had a certain size, but when you actually then enter the dust phase, the Hubble constant actually changes its evolution. I draw the graph on the next slide, and now the vectors can be larger than the horizon radius. So in fact, they'll have an extra energy, and the extra energy we already said. Let me just try to go a little quicker on these slides because I just want to finish on time. If we just put in the fact that we said before that the H square is order of G times the closure density, we already said this in words before, a vector of the size of the horizon, if you stretch it by order unity, gives an extra energy of this order. You compute energy density from this, and you check it's of order the closure energy density with some factor of order. Okay. So that's the kind of energy you get if your vector goes outside the horizon and it stretches. So then here I just plotted on a graph. As time progresses, the beginning you had the radiation phase, then you had the dust phase. We use T star to denote the time when radiation changed over to dust. And if you look at the graph of the horizon radius, at the beginning it was going like this, and then it actually ends up going like the red line is the horizon radius. It sort of turns around like this. But if you look at the size of the vectors, it was actually less than the horizon radius all the way in the radiation phase. We showed that. But in the dust phase, they can actually overshoot. And now these guys are outside the actual horizon radius, and they can stretch. But how much energy do you get from that stretching? Again, if the stretching was adiabatic, you just adjust to the new vacuum, like we showed right at the start of the talk for the mesons. You adiabatically increase the volume of the universe, you just get new vacuum fluctuations in the new universe and no stretching of anything. If you had a completely sudden stretching, you just have an enormous energy of order the closure density. The actual transition at T star is neither adiabatic nor sudden. It sort of happens over a couple of crossing timescales. So you expect a fraction, maybe a few percent of the closure energy density to come up in the stretching of vectors. And that seems to be the right amount of extra energy. Suppose you got 10%. Now I'm just putting words. I don't know how to get any given number out of this. But if you could get about 10% of the closure energy density from the stretching of these vectors when you transition from the T to the half to T to the 2/3, which is where we expect some stretching to happen, that extra energy, well, if you have that much of energy, it's called early dark energy, EDE. It would resolve the tension, people have argued, between the values of the Hubble constant, which you observe from late time and early time data. You actually find that around the time of transition between the two epochs, which is Z equals 2500, that redshift, measurements of local objects give this value of the Hubble constant, while the lambda CDM model applied to the cosmic microwave background gives this value, and this difference getting to be about 3 sigmas, getting to be a little uncomfortable. So one finds that if you had extra energy at this scale, people have argued it can resolve this tension, but we have found exactly when you change from radiation to dust, there is some extra energy you would get from these vectors. So it's interesting to argue if that could help us here and resolve this puzzle. It's purely a conjecture. We don't know actually how to get any numbers out of this, just the right scale. We've also noticed that the extra energy is of the scale of the closure density. Suppose that what happens after some time is that because you have some extra energy, you might get into a situation where the extra energy now drives the expansion. As you're expanding, the vectors stretch, and that puts in some energy. And if the energy from the stretching of the vectors drives the expansion, then in fact, you can get to a self-consistent situation where you no longer need any energy from the radiation or the dust to maintain the expansion, and you'd get into a universe phase which is purely supported by dark energy. You could do the same thing in the phase of inflation, because if you look at what happened in all the previous cases we have studied, whenever the pressure dropped, either from radiation to dust, or in the earlier case, radiation to dust, that's when the Hubble radius changes in such a way that the vector size goes outside the horizon, they start stretching, and you get this extra energy. But at the gut scale, all the guts energy particles, the heavy particles of guts, well, they froze out and the pressure dropped because you only got left with the standard model particles. Well, then the same thing would happen. And then you can again be left with a situation where the vectors stretch, they give you an extra energy of the order of closure density, and just this energy of the vectors can then just power your inflation by again putting you in an exponentially stretching phase. Okay, so these are all just possibilities, but they're all very interesting because all we have argued is, we just summarize in a couple of slides, the old picture of quantum gravity where all the fluctuations happen at the small distance scales really cannot work because the information paradox can be now made into a rigorous theorem and you cannot get out of the information puzzle then. You're forced to this new picture where you have virtual fluctuations of these virtual fuzzballs of all sizes. It resolves the information puzzle because it tells you that how these fuzzballs can form out of the collapsing dust ball. But then it also tells you that in cosmology, they give you extra energy at various length scales, at various epochs, which whenever the pressure is dropping, so they may just about be powering these extra energy scales that we don't understand where they come from in cosmology, and they may explain to us by having a beautiful interplay between the black hole puzzle and cosmology, they may explain to us all the missing things that we don't understand in cosmology. So thank you very much. I'll stop there.